Welcome to another episode of the AI Frontiers podcast, a product of the ArXiv preprint server. Today, we are exploring the most recent developments in artificial intelligence and machine learning research. Our focus is on papers from CS.LG, a category that stands for computer science, learning. This field captivates by creating and analyzing algorithms that machines can learn from and use to make data-based predictions. It forms the foundation of modern AI systems, from understanding complex patterns to automating decision-making and predicting future trends. Today's research themes are centered around the integration of physical principles into machine learning models. This approach, often called physics-informed machine learning, is designed to enhance the accuracy and predictive capabilities of these models. A remarkable example is the study by Patel and colleagues in 2025, where they applied this concept to metal additive manufacturing. Their work demonstrates the possibilities of optimizing the manufacturing process using hybrid systems. Another key theme in the current research is the use of deep learning for forecasting. Deep learning, a subset of machine learning, uses artificial neural networks to mimic the structure and function of the brain. These networks are exceptional at recognizing patterns and making predictions. For instance, Zhang and his team, in 2025, utilized deep learning techniques to predict wind power. Another example is Rashidi and his team's work, where they combine deep learning with other techniques for accurate gold price forecasting in financial markets. The third theme touched upon is the use of strategies like transfer learning and data augmentation to manage shifts in machine learning model domains. An example of this is the work of Zhang and his team, who proposed a physics-preserved transfer learning method. This method corrects domain shifts and preserves physical information within the model, thereby enhancing the versatility and robustness of machine learning systems. Reinforcement learning for energy management is the fourth theme. An example of this is Sumayli and colleagues' development of a home energy management system. This system uses deep reinforcement learning to adapt to changing user preferences, marking a significant step towards sustainable and user-friendly energy systems. Machine learning is also making significant strides in obsolescence forecasting, a critical aspect of supply chain management. For example, Saad and his team used deep generative modeling to generate new obsolescence cases, which improved the performance of their forecasting model by augmenting their training dataset. Patel et al.'s work on physics-informed machine learning in metal additive manufacturing particularly stands out among the key findings. By integrating physical laws into their model, they significantly improved the predictability and scalability of microstructure modeling in this field. This development overcomes the limitations of traditional data-driven approaches. Another key finding is Rashidi et al.'s successful application of a hybrid model for predicting gold prices. This model, which combines time series methods, regression, and artificial neural networks, outperformed traditional methods, opening a new chapter for high-accuracy forecasting in financial markets. Lastly, Sumayli and his team's deep reinforcement learning-based home energy management system showed promise for energy consumption optimization. Their model dynamically adapted to user preferences and achieved near-optimal performance. It also proved to be more computationally efficient than traditional methods. Across these studies, a mix of traditional techniques like regression and time series prediction, and advanced methods like neural networks and transformers, were employed. While these advanced techniques offer high accuracy and adaptability, they often require large datasets and substantial computational resources. Moreover, they function as black boxes, providing limited insight into their inner workings, which can be a hurdle to interpretability and trust. As a deep dive, let's look at Patel et al.'s seminal work. They presented a comprehensive evaluation of modeling strategies for microstructure prediction in metal additive manufacturing. The researchers highlighted the limitations of traditional methods and proposed physics-informed machine learning as an alternative. They demonstrated that incorporating physical laws into machine learning models could enhance accuracy, transparency, data efficiency, and extrapolation capabilities. Rashidi et al. Introduced a hybrid model for predicting gold prices in financial markets. Their model, which combines time series prediction models, stepwise regression, and artificial neural networks, outperformed traditional methods. This work underscores the potential of hybrid models in financial market predictions. Sumayli and his team proposed a home energy management system using deep reinforcement learning. Their system adapts to dynamic user-defined preferences and indicated a promising future direction for smart home technologies. Looking into the future, advancements in hybrid models, transfer learning, and data augmentation techniques offer promising avenues for overcoming challenges and pushing the boundaries of machine learning applications. However, challenges persist in terms of data requirements, computational resources, and model interpretability.